Okay, that's the rule. Amo, Bessie, Bishop, Bragg, Claudio, Chestnut, Coolwood. Yeah. Erlinson. There. Gerard. Green. Kennedy. Leonard. Mohammed Boy. I think that's seen. The boy's name. That's it here. Boys here, okay. Small, Sullivan, and Swiss is here. Okay. All right, so we're gonna start. Oh, before I begin chapter 6, I made the announcement already yesterday, but I'm gonna say it again. I was not able to download your, for some reason, I don't know, it seems as if it's on the end of Canvas, the company itself. I don't know what it's going on, but I had a hard time downloading your assignments. And as a result of that, I was not able to complete grading them before the weekend was ended. In fact, we're here, I'm still in the middle of grading them. I was able to download it later on. So what I've done is post the answer key, so that would help you to review for your test. And just to remind you, your test coming up on Thursday will cover assignments 3, 4, and 5, right? I've already sent back to you assignments 3 and 4, your graded assignments. Assignment 5 is the one that I'm in the middle of grading right now. And I'm hoping to get that back to you by this evening or by the latest tomorrow morning. But in the meantime, you can use the assignment key that I've published online, so that you can help, that can help you in terms of preparing for your test, right? Okay, so with that said, let's move on now to a discussion of thermochemistry, which, as the name suggests, basically talks about energy changes that occur in a chemical reaction, all right? So as such, we need to first talk about what we mean by this term energy, right? And the definition of energy is simply the capacity to do work. So this begs the question, what is work? Well, work is basically done when force is applied to an object and the object moves. So that's why it says here, work involves the displacement or movement of matter, right? Now, the original meaning of the word energy, I don't remember if it comes from Latin or Greek, but basically literally means work within. However, work is not something that an object can contain, all right? Now, under the broad heading of energy, there are two types. You have potential energy, which is the energy an object has by virtue of its position or composition. And then you have kinetic energy, which is the energy an object has by virtue of its motion, all right? So pretty much all forms of energy can fall into those two different categories. Now, as far as kinetic energy is concerned, we can easily calculate it by using this formula that you see here. Kinetic energy is equal to half mv squared, where m is the mass in kilograms. Write this down here. M is mass in kilograms. And V is the velocity in meters per second, right? So based on this formula here, right, we can say that the units of energy would be kilograms meters squared per second squared, right, based on the arrangement of the different terms in that equation. But there's one unit that is used to represent that collection of units, and it's called the joule unit, right? So 1 joule is equal to 1 kilogram meter squared over second squared, right? So that is basically the SI unit of energy. Now, there is a non-metric unit of energy known as the calories. We're going to look at that later on. So that's it as far as the units of energy is concerned. Okay, so let's talk about some basic terms in thermochemistry. As I said before, thermochemistry is that area which deals with the study of energy changes that will occur in a chemical reaction. So there are some terms that we use in this area. One is called the system, and the system is basically that part of the universe being studied. So the system could be, for example, what's going on in a test tube, or what's going on in a tank, or even what's going on Earth itself, because Earth is a part of the universe, right? So basically, all for whatever part of the universe that we are studying and we're interested in, that is called a system, right? And then, of course, the rest of the universe, we call that the surroundings, all right? Now, when it comes to systems, there are three main types of systems. You have what are known as open systems, where you have energy and matter being exchanged between the system and the surroundings. Then you have closed systems, where energy can be exchanged, but no matter can be exchanged between the system and surroundings. And then the final and third category are isolated systems, where there is no exchange between the matter inside and energy between the system and the surrounding. All right, so these are basically three definitions or three different types of systems. All right, and an example is shown here. This looks like a bottle of honey, right? Sealed, right? So therefore, we say that this is a system that's closed, because you can't have the exchange of matter between inside and outside the bottle. However, you can have energy exchange between inside and outside. So for example, you can heat the outside, and some of the heat will be transferred through the walls of the bottle into the whatever is present inside the bottle. All right, so we call this a closed system. Then a question is being asked here. After the lid of jar is unscrewed, what kind of system is it? So what do you think the answer to that question is? An open system, exactly. Okay, so let's talk about internal energy, another term that I need to introduce to you. And this is the total energy that's contained within a system. And there are two types of energy in this regard. Part of the internal energy would be kinetic, which has to do with the molecular motion, right? And when it comes to molecular motions, there are three main types. You have translational, rotational, and vibrational motion. Now, translational basically means that the molecules are moving in a straight line fashion. Rotational is talking about the molecule rotating around a particular axis. And vibrational, this has to do with atoms connected to each other in a bond, and they vibrate like this, right? Based on the amount of energy that they might have at that time, right? So all of these are related to what are called thermal energy, right? And this is actually related to the temperature. So basically, the higher the temperature, the greater the kinetic energy part of the internal energy. And that means more vibrational energy, more translational, more rotational, and so on, all right? So that collectively would be thermal energy, right? And then we have the other part of the internal energy, which is a potential energy, and these are basically intermolecular and intramolecular force of attraction and locations of atoms that have bonds, right? And we call these energies sometimes chemical energy, all right? So basically, when it comes to internal energy, there are two types, thermal and chemical. Thermal relates to kinetic energy of the particles, and chemical relates to the type of energy which is required to hold atoms together or ions together in a bond or by a bond, all right? Okay, so those are just some new terms that you need to know when you're dealing with thermochemistry. Another term we need to talk about is heat, right? Heat is a form of energy, but to be more strict about definition, the definition is right here. It's the energy transfer between a system and its surroundings caused by a temperature difference, right? So if there's a temperature difference between the system and surrounding, then basically the energy will flow from the region of higher temperature to the region of low temperature. And we call that energy the heat energy, which is transferred as a result of that temperature difference, right? Now, going back to what we said about thermal energy, remember I said that the thermal energy is as a result of the energy that is possessed by moving particles, atoms, molecules, and so on, right? And what you'll find is that when you have the heat transfer from one system to another, that heat transfer will continue right, from the more energetic molecules as demonstrated here in this diagram. We have argon here, which is more energetic than nitrogen on the other side of this hypothetical thin wall, right? So basically the energy transfer will come from the argon bombarding the walls, the argon molecule bombarding the walls, and the nitrogen on the other side will pick up some of that energy. That energy transfer will continue until we reach what is called a state of thermal equilibrium, right? And under those conditions, when we have thermal equilibrium, what will happen is that the temperature of both sides of this hypothetical thin wall will remain the same. And therefore, there will be no more transfer of heat energy from the argon to the nitrogen. So here's a very interesting question being asked here. And it relates to something that we talked about in the previous chapter, dealing with the root mean squared speed of atoms and molecules and so on. So the question says, how do the root mean squared speeds of the argon atoms and the nitrogen molecules compare at the point of thermal equilibrium, right? So at the point of thermal equilibrium, the kinetic energy of the argon would be equal to the kinetic energy of nitrogen, right? Now, if you remember, the formula for the calculation of the kinetic energy is, and this is true for both argon and nitrogen. In the case of argon, it's half mv squared for argon, right? And this would be equal to the formula for the kinetic energy of nitrogen would be half mv squared for the nitrogen, right? So, oh, by the way, I should have put here argon here for the mass MAR, and I should put Mn2 here because the masses will be different. Now the halves here will cancel out here and here, right? And what the question here is asking for is how do the root mean squared speeds of the molecules of argon atoms and the nitrogen molecules compare at the point of thermal equilibrium, right? So what we have to do is rearrange this equation here so that we end up with the speed of argon squared divided by the speed of nitrogen squared. That would be equal to the mass of the nitrogen divided by the mass of the argon. All right. So basically, to get, oh, by the way, this should be squared here. So therefore, we can actually put the numbers in for the mass of the nitrogen and argon. Nitrogen will have a molar mass of 28.02, and the argon will have a molar mass of
39.94.
39.94. So whatever that ratio gives you, that would give you the ratio of V squared to, V squared of argon divided by V squared of nitrogen. So to find the actual ratio of the velocity of argon compared to the velocity of nitrogen, that would be equal to the square root of 28.02 divided by 39.94. So if I were to do that calculation, 28.02 divided by 39.94, and then find the square root of that. And according to my calculation, this works out to be equal to 0.838, right? So that would be the ratio between the velocity of the argon atoms compared to the velocity of the nitrogen molecules, right? So basically the argon atoms will be traveling at a slower speed compared to that of the nitrogen molecules. All right, okay. So that's basically dealing with heat and the relationship between the root mean squared speeds of atoms if the thermal equilibrium, when they both achieve thermal equilibrium when separated by a thin hypothetical wall. Okay, so the other term that I need to introduce to you, I mentioned it briefly before, work. Work is kind of similar to heat. It represents an energy transfer, but the difference is that the energy transfer in this case is not due to a temperature difference, right? It is actually due to a force, right? Now, remember we said that work is basically what is done when force is applied to an object and the object moves a distance, right? So that's what work is. So if you apply force to an object and it doesn't move, then you're not doing work, right? But the object has to move under the influence of that force in order for work to be done, right? So if you do that to an object, work is done on the object, then that object will gain energy as a result of that. Now, the opposite would be true if the object does work on something or on the universe or on the rest of the universe or the surroundings, right? In that case, the object will lose energy and therefore its value would be negative. And what we're going to see is that the sign will be very important when it comes to doing certain calculations, when it comes to work and heat energy and also overall energy. But just to focus on the application of signs when it comes to work, if it's negative, that means that the system is losing energy, right? That means that the system is doing work on the surroundings. If the system gains energy, that means that energy is positive, or the work that is done on the object is results in positive energy or gaining energy of the system. All right. So very important that you understand what those two terms mean in terms of their sign. Now, please note there's no such thing as negative or positive energy, right? It's basically an indication as to how the energy flow with respect to its direction, right? So if energy is flowing from an object, then mathematically speaking, we say that that energy is negative relative to the object. Now, relative to the surroundings, the energy will be positive because that system or that surroundings will be gaining the energy, right? And the same is true as you're going to see shortly for heat, all right? You can have negative heat and positive heat, and we're going to see some applications of those signs when it comes to changes in energy as due to work or due to heat energy, all right? Now, let's look at this hypothetical situation. So imagine you have this setup where you have a gas trapped in a container. You have this movable plate here. Let's assume, I mean, this is, of course, won't happen in reality, but let's assume we live in a perfect world where this plate can move up and down without any friction, right? So you have your gas trapped inside here, right? And let's say that the gas gains some energy so that it expands, right? So therefore, there's going to be a change in volume, right? So this would be the initial volume represented here. This would be the final volume here, which would mean that delta V, the change in volume, would be equal to V final minus V initial, all right? So how do we calculate the work that is done by the gas, right? Basically, the work that is done by the gas is given by this equation right here. We're assuming that the pressure of the gas is constant, right? So basically, the work done by the gas would be minus P times delta V, all right? And because V final is greater than V initial, that means that work would be negative. Do I have that here? No, I don't. Okay, so let me put that here. So because V final is greater than V initial, that means that work would be negative, right? So basically the system is losing energy by expanding against the surroundings, all right? V final minus V initial will be positive, delta V will be positive here, but because of this negative sign, the W will be negative, okay? So that's what happens when the gas expands against the surroundings, all right? Okay, some other terms I need to introduce to you here. State function, or let me start off with the state of a system. Now, before, and I wouldn't blame you for this, you would have learned that there are three states of matter, right? Solid, liquid, and gas, right? So I'm quite sure you're familiar with the term state in regards to the phases of matter, right? However, strictly speaking, state, that term state is actually more encompassing, right? As stated here, it is the exact condition at a fixed instant, all right? And it says here further that the state is determined by the kinds and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. So let me give you a couple of examples. Let's say, for example, I have water, liquid, at, let's say, 15 degrees Celsius, right? And I raise the temperature of water which would still be the liquid state, to 30 degrees Celsius, right? Believe it or not, even though it's still in the same liquid state, strictly speaking, based on the definition of the state I gave here, right? This water here at 30 degrees would be in a different state compared to the water at 50 degrees, simply because the temperature changes, right? So if the temperature change, right, for a substance, then at the new temperature, the state will be different compared to the old temperature. Let me give you another example. Let's say I gave you a situation where oxygen gas has a pressure of, let's say, 2 atmospheres, and I change the pressure of that gas to 5 atmospheres, right? Again, 2 different states, right? Simply because you change the pressure, all right? Even though in both states, they're in a gaseous state, so to speak, but because the pressure is different, then there's a change in state that is observed here. And that is true even as it says here for the amount of matter. Let's say I have sodium, which is a solid, and let's say I have 2 grams of it, and let's say I increase the amount of sodium to 3 grams, right? That's a change of state as well, simply because I'm changing mass, right? So that's what the term state means, right? Basically, it is the exact condition at a fixed instant, and it's determined by different factors, properties, whatever. Could be temperature, could be pressure, could be the amounts, could be structure, and so on and so forth, all right? Now, let me get rid of this here and continue with another term that I have to introduce to you, the state function, which is a property basically that has a unique value that depends on the current state of the system. And this is very important, does not depend on how the state was reached. In other words, it does not depend on the history of the system, all right? So you're going to meet several state functions in this chapter, which, are basically numerical quantitative measurements that depends on the state of the substance, depends on the pressure, temperature, the amount of matter, the mass, and so on, all right? So this law, let's talk about this law. I don't know if you've met this law before. It's called the law of conservation of energy, also known as the first law of thermodynamics, which says that in a physical or chemical change, energy can be exchanged between a system and its surroundings, but no energy can be created or destroyed, all right? And we're going to see how this law applies to certain problem-solving exercises. All right, so this is the first law. Simply put, if you want to abbreviate it in a simple way, energy cannot be created nor destroyed. But you need to understand that this only applies to physical or chemical processes. For those of you who have to do general chemistry too, when you get to the chapter dealing with nuclear chemistry, you'll see that you can actually have energy created or destroyed, but that would happen in a nuclear reaction, right? So what we're talking about here, as far as the first law of thermodynamics is concerned, relates to chemical and physical changes, right? So the inference we can come to based on this law is that the internal energy of a system is simply the difference in the energy between its initial and final state. In other words, the difference or the change in internal energy is equal to the internal energy of the final state minus the internal energy of the initial state, right? And there's an additional inference which talks about the relationship between the change in internal energy, heat, and work. And it is given by this equation right here. Delta U is equal to Q plus W, right? So delta U is a change. Let's see if I have that here. Okay, so delta U is the change in internal energy. Internal energy. Q is the heat change. And W is equal to work done on the system. Work done on the system, all right? So those are the 3 terms in this equation here, all right? So basically, whenever a substance or a system is undergoing a change in internal energy, it is some combination of heat change and work done on the system. Now, in some cases, there might not be any work done, which means that internal energy will be equal to the heat change, right? I can't think of any situation that Q would be zero, the heat change would be zero if there's a change in internal energy. It may be possible, but you know, I'm no expert in thermodynamics, so won't say anything about that, all right? Okay, so that's the relationship between delta U, Q, and W, right? Now, as I said earlier, it's very important that you understand what the signs of these values represent, right? And what you're going to see is that there are some questions which deal with this equation where you have to be careful when interpreting the question so that you use the appropriate signs for Q and W. So let's talk about the signs and what they mean when it comes to that equation, right? Whenever you have energy entering the system by any means, right? Then the sign for that energy change will be positive, right? So if a substance is absorbing heat, then basically Q is going to be positive as far as the system is concerned, right? If work is done on the system, then W will also be positive from the perspective of the system, all right? So energy entering the system can occur as a result of heat being absorbed by the system or work done on the system, all right? And then the opposite is true if energy is leaving the system. What that means basically is that you can have heat leaving the system, right? In other words, heat transfer from the system to the surroundings and work done by the system on the surroundings, all right? So it's very important that when you're reading questions, you try to see whether or not, if the question is dealing with this sort of system, whether or not the heat being expressed in the question or the W being expressed in the question is positive or negative. So here's an example of this. The question says a gas does, now please know the terminology, a gas does 135 joules of work while expanding, and at the same time it absorbs 156 joules of heat. So the question is asking, what is the change in internal energy? So remember, the equation is delta U is equal to Q plus W, right? So my question to you is this, based on, let's deal with the work part. Based on how the question is worded, would you say that the work is negative or positive? Because the question says the gas does 135 joules of work. So would you say that the work, the 135 joules, would you say that that should be expressed as a positive number or a negative number? Negative, right? So therefore, in this equation, you're going to have minus 135 joules of work. And then the question goes on to say, at the same time, it absorbs 156 joules of heat. So would that be negative or positive? Sorry? Positive, exactly. So that would be positive 156 joules of heat. So we just add these two together, and the answer would be 156 minus 135. So according to my calculation, this works out to be equal to 21 joules. All right. So this is an example which underscores the importance of interpreting the question carefully so that you use the appropriate signs for both work and heat. All right. Okay, so let me give you this assignment here, and I want you guys to focus on questions 1 and 2. And for you guys out there in Zoom, I'm going to publish the assignment I just handed out here in class. Let me go here. Go here. Here. Let me go here. Just go down. Oh, I just remembered. There are 2 links. I'm going to publish both of them. All right. For assignment 6. But you don't need this one right now. The one in fact, hold on, let me check something. What did I hand out to you? Okay, so what I handed out to you guys in class was both of them, right? The last one here is the last page that I stapled, all right? But for now, for you guys out there in Zoom, you don't really need this. This is what we'll be focusing on. So let me download that right now. Okay. So, as I said before, we'll be focusing on questions 1 and 2. Let's start off with 1. It says the total change in internal energy. Where they use delta E here, delta U is the same thing, right? Of a system, you can calculate that, of a system, when 400 joules of heat is applied to expanding oxygen, and the gas does 350 joules of work on the surrounding. So, same equation, we're going to use delta U is equal to Q plus W, all right? So what is Q based on the information provided in the question? 400 joules, and that would be what? Positive or negative? Positive, exactly. Minus, well not minus, I'm sorry, plus, what would be W? Minus 350 joules, exactly. And that's it. So 400 minus 350 gives you 50 joules. And that's it, all right? Okay, so that's number 1. Number 2 is asking for us to calculate the kinetic energy in joules, calories, kilojoules of a particle, and it gives you the mass and it gives you the velocity. I didn't mention this, so let me do so now. Let me clear this first. I didn't mention the unit, calorie unit, which is another unit of energy. It's not the metric unit of energy. And the calorie unit, let me just write down the relationship between the calorie and the joule. 1 calorie is equal to 4.18 joules. And you can find this, of course, in the packet that I've posted in Chem, right? So that's, you're going to need that in order to answer the calorie part here, all right? But let's focus on calculating the kinetic energy in joule. Now remember, the formula I gave you is kinetic energy is equal to half mv squared. Remember I said that the mass must be in kilograms and the velocity must be in meters per second, right? So if I were to apply that formula to calculate the kinetic energy in joules, that would be equal to half times the mass in kilograms. Now they gave us the mass in grams, right? 9.11 times 10 to the minus 28 grams. So what we have to do in this case is convert that to kilograms. 1 kilogram above, 1,000 grams below, right? And then we do the number crunching. Oh, no, then we multiply by the velocity, which is 6.00 times 10 to the 5 meters per second squared. And then we do the number crunching, right? So let me do the 6.00 times 10 to the 5 squared first, and then multiply that by 9.11 times 10 to the minus 28, and then I multiply that by 0.5, and please correct me if I'm wrong, but the answer I got is rounded off to 3 sig figs, 1.64 times 10 to the minus 16, and the units here would be joule, because remember I said, well, firstly, the gram units will cancel out here and here. And remember I said that the joule unit is the same thing as kilograms, meters squared over second squared, all right? So that's basically how we do the calculation of the kinetic energy in joules, right? Any questions so far? Any questions? Any questions? Yes, sir.
Where did the 4.8 joules?
That is a given. That's a definition. That's a defined relationship between the joule unit and the calorie unit.
But do we use that?
You're going to use that in this part to get the energy in calories, right? And the way we do that to get energy in calories, we're going to start off with the 1.64 times 10 to the minus 16 joules. And we're going to multiply that by, down here, we're going to put 4.18 joules. And up here, we're gonna put 1 calorie. And that will give us the answer in calories, so 1.64 times 10 to the minus 16 divided by 4.18. And according to my calculation, again, please tell me if I'm wrong, but according to my calculation, the answer is 3.92 times 10 to the minus 17 calories. And that's how that is done, all right? And then the question is asking for the energy in kilojoules. So how do you think we will do that? Let me just draw a line here. Start out with 1.64 times 10 to the minus 16 joules. So how do we convert from joules to kilojoules? What does kilo mean?
1,000 joules.
1,000, right? So we're going to put 1,000 joules down here and 1 kilojoules above. And let's see what that gives. Well, I can't say what that gives 1.64 times 10 to the minus 13 kilojoules. And that's how that is done, right? Okay, any questions about any of these? Yes, sir.
What was the formula that you used? I can't see it.
You mean this formula right here?
Yeah.
Right, that's a formula for calculating the kinetic energy directly. And remember, please, when using that formula, the mass must be in kilograms. Right? That's why I converted from grams to kilograms here, right? And the velocity must be in meters per second, which is already given.
So what is the formula say? It's 1/2.
Half times m, the mass, times the velocity squared. All right? Okay, any other questions about this? Any other questions? I'll give you a minute to copy that. In fact, in the meantime, let me see who is here currently. Okay, Hamill here. Hamill here. Brad
Here.
is here. Chestnut. Green. Kennedy. Leonard. Small. And I think that's it. Okay. Let me get out of this here. I guess I can clear it, right?
Yeah.
Okay, let me go back to the PowerPoint and what's next? Okay, so let's talk about heats of reaction. And heats of reaction is basically the amount of heat that is exchanged between the system and surroundings while a reaction is taking place, right? So what you'll find is that in some cases, the reaction will produce heat. In other cases, the reaction will absorb heat from the surroundings. Now, the difference between these two can be used, there are terms you can use to distinguish between these two types of reactions, right? So if you have a reaction which gives off heat, right? We say that that reaction is exothermic, okay? And what that means is that in an isolated system, the temperature will increase and the system will go from a higher to a lower energy, right? So basically, if you start off with the reactants and as the reaction takes place, it produces products and heat is generated. When you compare the energy of the products to the energy of the reactants, the energy of the products will be less, all right? And I can give you a simple example of this. If you take, for example, a test tube with water and you add a few granules of sodium hydroxide to it, depending on the amount of sodium hydroxide, if you feel the outside of the test tube, it's going to feel warm or even hot, right? And the reason why is that when the sodium hydroxide dissolves, it generates heat, right? And therefore, the heat is given off to the environment, and that's why you can detect it when you touch the outside of the test tube. On the other hand, you can have what are known as endothermic reactions, and these are reactions which absorbs heat from the surroundings. And as stated here, in an isolated system, the temperature will decrease in this case. And if you look at the reactants, the products, in terms of the energy changes, what happens is that the energy of the products would be greater than the energy of the reactants. And again, I can describe an example of this. If you have a test tube, and this time, instead of adding sodium hydroxide to it, you would add, let's say, ammonium nitrate or potassium nitrate or sodium nitrate, any one of those would work. What will happen is that if you feel the outside of the test tube, it's going to feel cold, right? And that's because when those substances dissolve in water, it absorbs heat energy from the environment, and therefore, when you touch it on the outside, it feels cold, right? So basically, all reactions can be put into one of these two categories, exothermic or endothermic. And to look at this in more detail, we're going to look at this hypothetical situation. So let's say we have these three situations here. This is definitely a hypothetical situation where we're assuming that, okay, first of all, we're assuming that the reaction taking place in each of these containers are exothermic reactions, generates heat, right? And in this hypothetical situation, we're assuming that all the heat generated will simply be transferred to the surroundings, right? This is highly unlikely to occur, right? Because there will be some absorption of the heat by the contents left inside the container. But let's say we're going to work with this, right? If that happens, then the temperature will remain steady at 25 degrees. We're assuming that the surroundings temperature will be 25 degrees because all the heat generated here will simply go into the surroundings, right? Now, in this case here, right, which is more realistic, if you have a reaction in a beaker, let's say, or a test tube, what will happen is that some of the heat energy generated will escape into the surroundings, while the other portion of the heat generated will contribute to the increase in temperature. So the temperature of whatever is left here will increase to a value above 25 degrees Celsius, in this case, 32.2 degrees Celsius, right? So that's what is more likely to happen compared to this purely hypothetical situation. And then now, if we're dealing with an isolated system, right? Here we have two styrofoam cups. Styrofoam is an insulating material, right? So therefore, it will not allow for the escape of any heat energy. So what's going to happen if this same reaction took place in this particular isolated system? The temperature will be even higher. Whoops, sorry, because all the heat is now basically trapped into that system, and therefore the temperature will be higher compared to the previous system right here, where some of the heat will be allowed to escape, right? So in an isolated system, all the heat will be absorbed by whatever is left inside that container. So basically, that is what will happen in these three situations if the reaction involved is exothermic. And if you understand this, then you should be able to appreciate what will happen if the reaction is endothermic in each of these cases. So I'm going to leave that for you to consider on your own. And if you have any questions about that, you can let me know. All right. Okay. So let's talk about energy changes under different conditions. Again, we're going back to this equation right here. And in this particular case, we're talking about a situation where the energy change will occur if the volume remains fixed, if the volume is constant. Now, if the volume is constant, that means, let me go back to this equation right here. W is equal to minus P times delta V, right? If the volume is constant, that means that delta V is equal to 0, which means that the work is equal to 0, right? And if delta U is equal to Q plus W, if W is equal to 0, that means that delta U is simply equal to the heat change of the system, right? And you see that they put V here as a small subscript. Basically what that means is that the volume is constant, right? So basically what we can conclude is that if the volume remains constant in this sort of system, then the internal energy change is only due to the heat change of the system, right? There's no pressure volume work being done by the system or on the system in that particular situation. Now, this is less likely to occur in reality, all right? It's less likely, it's very unlikely that you can have naturally a system where the volume remains constant, even though it's possible to set up an experiment where that's the case. But in most experiments, most reactions that is taking place, the volume of the system is not held constant, all right? What is more likely to happen is if the pressure is constant, and that's what we're gonna look at now. What happens as far as the internal energy changing under the conditions of constant pressure, right? So in that particular case, we cannot say that delta V is equal to 0, right? Because there will be a volume change in that particular system, but the pressure will remain constant, right? So basically, this is the equation that will result. The change in internal energy is equal to the heat change under constant pressure minus the pressure times the change in volume. And we can rearrange this to get the heat change under constant pressure is equal to the change in internal energy plus P times the change in the volume, right? And this is more likely to be a more realistic scenario when it comes to carrying out any chemical reaction, right? Pretty much, basically, the heat change would be due to two changes. One would be the internal energy change, and the other would be the work change or the work that is done on or by the system, all right? Now, most of the thermal energy released will be released as heat, all right? And it says here some work is done by the system when it expands against surrounding, and that's this part right here, P times delta V, all right? So that is what happens under constant pressure conditions. Okay, so this leads us to a discussion and an introduction of another term known as enthalpy, right? So the definition of enthalpy is the sum of the internal energy and the pressure volume product of a system. So this is the formula that is used to calculate enthalpy, all right? H is the enthalpy, that is equal to U, which is the internal energy, plus P times V. P is the pressure, V is the volume, right? And if you want to look at a situation where there's a change in pressure and change in internal energy, then that results in a change in enthalpy, right? So we can, do I have it here? No, I don't. Okay, so we can write down a relationship between the change in enthalpy, delta H, and that is equal to the change in internal energy plus P times the change in volume. Again, P is going to be constant, all right? So an example is shown here of the application of this equation, the reaction between magnesium and hydrochloric acid to form hydrogen, right? As stated here, most reactions occur under conditions of constant pressure. So for most reactions, the heat that is produced is equal to the enthalpy change here. I'm mistakenly put delta H here. This should be delta U right here, right? Okay, so as you see in this reaction here, hydrogen is produced. The pressure of the hydrogen that is produced will basically do work against the atmosphere, against the surroundings, right? So that's the pressure in this particular equation here. There's also going to be a change in volume because the hydrogen is expanding. And there's also a corresponding change in internal energy, right? So that's how we can calculate delta H based on those different terms, all right? So that's the enthalpy of the reaction. Simply put, even though technically speaking, this is not 100% accurate, simply put, you can see enthalpy as the heat change, or in delta H as the heat change as the reaction is taking place, okay? All right, any questions so far? Any questions? Any questions?
So they're using H for heat instead of Q?
Right, exactly. In fact, it states here QP, which is the heat change under constant pressure, is equal to the change in enthalpy. All right. Okay. All right, let me see what's on the next slide. Okay, so let's talk about the properties of enthalpy because we've been using enthalpy a whole lot when it comes to solving certain problems. Because enthalpy, of course, is a measure of the heat change of a reaction. First thing I want to say here is that enthalpy is an extensive property, which means that the enthalpy of a reaction is dependent on the amounts of substances involved in the reaction, right? So if a reaction, let's say, involves 1 gram of a substance and it produces a certain amount of heat, then if you change the mass to 2 grams, everything else will be the same. then the amount of heat change occurring would be twice that the initial value, all right? So it's an extensive property. Another thing I want to say about enthalpy is that it's a state function, and the reason why is because the enthalpy is dependent on U, P, and V, the internal energy, pressure, and volume, which are also state functions, right? So because enthalpy is related to those terms, enthalpy is also a state function. And of course, the enthalpy changes in chemical reactions will have unique values, all right? And also, as stated here in the green box, because enthalpy is a state function, the enthalpy change depends only on the initial and final states. And we're going to see how that applies when it comes to problem solving exercises. Now, as far as the enthalpy values are concerned, they are for the most part measured experimentally, even though you can use certain measured values of certain reactions to determine the enthalpy changes in other related reactions. And we're going to see how that happens, right? Negative values indicate that the reaction is exothermic. Remember what we said about exothermic reactions. Exothermic reactions are a reaction that produces heat. So those reactions will have delta H being negative, all right? And then positive values indicate endothermic reactions. So that means that delta H, in the case of endothermic reactions, will be positive. And that is demonstrated in these two diagrams right here. The y-axis represents enthalpy, the x-axis represents progress of reaction. So in the case of an exothermic reaction, the products will have a lower energy compared to the reactants. And let me just say that the change in enthalpy, delta H, would be equal to the enthalpy of the products minus the enthalpy of the reactants. All right? So whenever you're looking at the change in enthalpy for any reaction, it's always the products minus reactants, right? So in this particular case, because the enthalpy of the products is less than the enthalpy of the reactants, then delta H will be negative, and that of course will be due to the fact that it's an exothermic reaction where the reactants loses heat energy to form the products. And the reverse will be true in this case, in the case of an endothermic reaction, where the energy or the enthalpy of the products will be higher compared to the enthalpy of the reactants, which means that delta H would be positive in that particular case because energy is absorbed as the reaction progresses from the reactants to the products. All right. Okay. Now, what happens if the reaction is reversed? Right. So let's say we have delta H being equal to a certain value for the reaction going in one direction. What happens if the reaction goes in the opposite direction? Well, the answer is very simple. The sign changes, right? So if the sign is positive for the reaction going in one direction, then the opposite sign would be applied for the reaction going in the reverse direction, but the magnitudes would remain the same, all right? So therefore, as a result, if you have a cyclic process, if you go from reactant to product, and then from product back to reactant, the total enthalpy change of that would be zero, all right? And here's an example. The decomposition of mercury to oxide. This is the reactant here. And if you heat it to form these products, this would be the enthalpy change, right? If the products become reactants and react to form the original substance, mercury to oxide, notice that the change of sign applies here. The magnitude will still be the same, but the sign will be different, all right? And this is also something that you need to be aware of when it comes to certain problem solving exercises, right? So basically, that's what happens when you reverse reaction. The sign will change, but the magnitude will remain the same. So let's see if we can tackle these two examples. Okay, so the first example says, you're given the equation, and it gives you the balance equation, and it gives you also the enthalpy change of the reaction. And then the question is asking for you to calculate the enthalpy change for the equation B, right? Now, my question to you is this. Excuse me. I want you to examine equation A and equation B closely. And I want you to tell me the difference between those two equations. And let me give you a hint. There are two differences between equations A and B. So what are those differences? Sorry?
It's the,
The
I was gonna say
H
the equations are flipped and the moles are divided by 2.
Okay, okay, so who was that who spoke? Is that you, Mr. Bassi? Or is that Mr. Swistat?
It's Mr. Basti.
Oh,
I was
okay.
gonna say the moles are divided by 2 and the equation's flipped.
Right, the coefficients are divided by 2. That's one difference, right? So like H2 and I2, their coefficients are halves, and HI, it's 1 here, whereas it was 2 here. And as he correctly said, the equation is flipped, right? So that the reactants in this equation are now the products in the second equation, and the product in this equation is the reactant in the second equation. Okay, so this begs the question, how does that change the delta H so that you can calculate the delta H for this reaction? Well, if you remember, we said that if you flip the equation, then the sign changes, right? So if I were to flip this equation here, right, I would get the sign so if the equation is flipped, 2HI to give H2 plus I2, then delta H will be equal to what? Minus 52.96 kilojoules, right? And then now, if I were to divide all these coefficients by 2, so this becomes half, and this becomes half, then I have to divide that by 2 as well, right? So the answer to this question is minus 52.96 divided by 2. And according to my calculation, this works out equal to 26, or I should say minus 26.48 kilojoules. All right? So that's basically how that is done. All right, any questions about this? Any questions? Any questions? Okay, so let's look at the second example. It says a complete combustion of liquid octane, and it gives you the formula, to produce gaseous carbon dioxide and liquid water at 25 degrees Celsius and at a constant pressure gives off, and please note the terminology here, gives off, what does that tell you? Huh? Not work, heat. It gives off 47.9 kilojoules of heat, right? So that tells you that heat is lost, which tells you that the reaction is
Exothermic.
exothermic. Exactly, the reaction is exothermic, all right? That's very important in answering this question. So let me see here. Write a chemical equation to represent this equation. Okay. Admittedly, that last line is not very clear. What the question is actually asking for is for you to write down an equation like this, including the delta H value, right? Based on the information that's provided here, all right? Okay, so let me, I think I'm gonna need some space. Let me move this up here. Oh, no. Okay, I think there should be no space down there. All right. So, first thing I would do is write down an equation and balance it. So can you tell me what would be the reactants in this equation?
C8H18.
Okay, so C8H18 plus, huh? Remember the question says it produces carbon dioxide and water. So carbon dioxide would be a product, would be products,
We need O2.
right, plus O2, all right? And then we need to balance it. So how would you go about balancing it? Here. Heat in front of the CO2. For 25.2. And then what we have to do next is we have to multiply everything by 2, right? So this becomes 2 C8 H18 plus 25O2 to give 16 CO2 plus 18 H2. So that will be the equation we have to work with, all right? Now the question says that the amount of heat given off is 47.9 kilojoules for every gram of octane, all right? So what we need to do is find out what delta H will be equal to based on that information and based on the balanced equation. So let me do this up here. What I'm going to do, since the equation here has a coefficient of 2 for the octane, so that will be 2 moles of octane. And what I will do is convert that to grams. So you're going to have 1 mole of C8H18. And down here or up here, I'd have to calculate the molar mass of octane. So that's 8 times 12.01 plus 18 times 1.008. And according to my calculation, this will work out to be equal to 114.22 grams of C8H18, all right? So by doing that, we're calculating the mass in grams equal to 2 moles. And then the next conversion factor will now take this information into account. Now, because it said it gives off this amount of heat, that means I would put minus 47.9 kilojoules for every 1 gram of octane, C8H18, all right? So let's see what that gives. 2 times 114.22 times 47.9 negative. So according to my calculations, I got minus 10. Let me do this in scientific notation. Minus here is here. Okay, so I'm going to say minus 1.09 times 10 to the 4 and kilojoules goes here, right? So this would be the enthalpy change that I'm going to put here, minus 1.09 times 10 to the 4 kilojoules. That would be the answer. That's how you do that. All right. Any questions about this? Any questions? Questions? Okay, so based on what we have done just now, let's go back to the assignments. And let's look at, oh, no, you can, oh, wait a minute, you're free. Okay, you won't be able to do any of these questions. So let me just continue the point. I thought number 3 would be something similar to this, but not quite. All right, okay, so screen, and then we go. Okay, let's talk about enthalpy change in stoichiometric calculations. We did one example of that actually just now, but basically, as you saw from the example I just did, when it comes to heat being evolved, we can consider that to be a product of the reaction because heat is generated. And if heat is absorbed, then we can consider it to be a reactant for the purposes of solving enthalpy problems. And therefore, we can generate conversion factors that involve the change in enthalpy. So for example, let's look at this reaction here. We can, based on this equation, in addition to the enthalpy change being given, we can represent the enthalpy change, or I should say, relationships between the moles of different substances and the enthalpy change, right? So for example, this is one conversion factor that we can use, minus 184.6 kilojoules divided by 1 mole of hydrogen, or the other way around, depending on the type of problem that you're trying to solve. And here we have another one relating the enthalpy change to chlorine. Here we have another one relating the enthalpy change to hydrochloric acid, right? So it depends on, the type of problem you're trying to solve. And it depends on the information you're given. But of course, I would say that one of the most important things that you need to make sure, and that is that the equation is balanced, because obviously, if the equation is not balanced, then these conversion factors could be incorrect. And therefore, any calculation based on those would be more than likely incorrect as well. All right. Okay, so let's look at this particular example. Again, I'm going to need some space. Let me bring this up here. So in this example, it says, what is the enthalpy change associated with this reaction? And the question gives you question gives you 5.67 moles of HCl. And the question is asking for the enthalpy change, presumably in kilojoules, right? So based on this equation here, there is a 2 mole ratio to this value here, right? So this is what I'm going to do. I'm going to start off with the 5.67 moles of HCl here, and I'm going to represent that relationship here in this between the parentheses here, and I'm going to put minus 184.6 kilojoules above and 2 moles of HCl below. This should be HCl here. So this will cancel out with that, and then you do your number crunching. 5.67 times 184.6 minus divided by 2. And according to my calculations, rounded off to 3 sig figs, the answer becomes minus 523 kilojoules. And that's how you do it. All right? Okay. Any questions about this example? Any questions? Any questions? Okay. What time is it? I think I'm going to stop here. Okay, I'm going to stop here for today, because this is an involved topic. All right, so just remind you again, your test is on Thursday. We'll cover chapters, what did I say, 3, 4, and 5.
Yes, sir. Can you post it past?
I think I did. Let me check and make sure. Let me check and make sure. Past it, okay, so let me see here. This here is a combination of tests 1, 2, and 3. Okay, so you can look for test number 2 there and look at those questions as well. And of course, I'm available during office hours. My office hours on Wednesday is from 2 to 6. I'll be at the Ocala campus, but you can contact me via Skype, right?
Thank you. Thank you.
No problem. Okay, for you guys all there in Zoom, I'm signing off.